Good morning, everyone. I hope you enjoyed the coffee break, and I hope you enjoyed the talk by Nico on progressive web apps. I'm going to touch a little bit on this, but I want to focus much more on the broader aspect of this project that we've been doing. So what happens when you put a group of technology enthusiasts on a mountain with a task to figure out how to get a forecast out of a box? And so their mission is then to experiment with technologies, to self-organize, to organize themselves, and set up the project in such a way that we have a product at the end that we could demonstrate and use. And I'd like to take you in this talk through that journey, showing you how we as a community worked together to accomplish this goal. Okay. So my name is Wicher. I'm from the Netherlands. I live in Switzerland, and I work as a developer and architect at Avni in Zurich. The project is about this dust measurement network. When we talk about dust, we actually talk about air particles. Not necessarily dust, as you know, that is lying on the ground. It could be different kinds of particles, different kinds of chemicals. And the idea of our project was to build an application for end users which they could use to monitor and predict pollution levels. And we would use that, we would do the prediction using machine learning, and we will collect these, the pollution levels using IoT devices that we connect to our cloud network. Because it's a grassroots community, we'll have to self-organize ourselves. We have to define roles. We have to identify what technologies are required, which ones we want to choose, which ones we want to pursue. And I'll talk you through this in this talk. So the idea, as I said, what happened there? Let's see. Okay. Let's get rid of this. Doesn't want to. Okay. All right, so a little fluke in the network. Always happens during a presentation, right? So the idea was to have and we came up with this in the early 2018. So early this year, somebody came up with the idea, like, hey, let's build a fully functional application or product that we can use to predict air quality or air pollution. And us as technologists, we wanted this to be as open as possible. We wanted to use open software. We wanted to share our data with the world, with communities, or with society. Of course, it should use sensors. We have to collect this information, and we want to distribute that information to individuals so that it's beneficial. We could use this in everyday life to, for example, decide whether we would take the car or the bicycle, for example. Now, this is a very vague idea. Like, how do we get from a product to this idea? And I'll explain you that. I'll walk you through this process. That's how we approached the development, or even the project leadership of this product. I'm going to touch on every aspect here, but I'm not going to go into very technical detail. I could, but it will take the whole day, and I only have an hour, and you also probably have questions. So I'm going to touch the surface, scratch the surface of these individual topics. I'm definitely going to talk about technologies, but I rather want to give you an overview of how do we approach this. So we have this idea, and we need to define what actually we want to do. And so we decided to organize an ideation workshop where we would define what is the product, what is our vision of what we want to build. From that product vision, we would create a minimal value product, or an MVP, that defines what actually we want to accomplish within that first iteration. We'll self-organize ourselves, and we'll design an architecture, then go to the actual development, so the hands-on productivity, which what I as a developer really love. I mean, all that other stuff is preparation. For me, it's about the architecture and development. Of course, also showing the results. We'll integrate all the individual components, and then in the end, hopefully, we have a demo. So that was our roadmap. So how do we get from this idea to a product vision? So we decided to enlist our innovation experts at Ernie. These people are very well at organizing, at brainstorming. They guide you into the direction of what you would like to accomplish. And there, we did a lot of brainstorming about, so what do we actually want to build? And so what kind of vision do we want to go on? What is this product that we actually want to have? What is this forecast that we want to provide to users? Lots of brainstorming, lots of wild ideas, going back, left and right, back and forth. Way too many ideas to even write down here on this sheet. There's already too many here. But in essence, it goes to, we want to be able to monitor air pollution. And we want to have that information live, somewhere available to the user. We would probably also want to see the evolution of pollution over time. So we want to have a sort of a time machine. When you're in a window, you can see how what the pollution at a particular location was. We want to be able to compare locations, for example, and correlate that to other sources. For example, traffic data or how the weather was, all these things. Of course, we need a sensor. We need to collect this information. We could use sensors that are already out there. We can benefit from those, but I think we thought it would be cool to create our own, and so that's what we decided. These are the sensors that are out in the field. They do remote sensing. They need to send the data to the application. So we need to have a cloud that combines all that information together and provides it to the web app. We want to use AI, machine learning, for the prediction. And here it's mostly about we want to provide early warning systems or SMS warnings to users that subscribe to this service, or help it with the route planning if you, for example, cycle and you don't want to go through polluted areas. Visualization, so UX, user experience is very important here. We want to give users a fun experience, a good experience. And so it's important here that we use clear visualization. It needs to be a responsive web app, so it's easily usable also on the mobile phone. We don't have to develop the UI twice or thrice. Important here also, like I said in the beginning, is that we want to contribute to society. We want the data that we collect and the forecasting that we calculate, we would like to share that with individuals or with communities. With developers, but also for let's say, regular people. And so we'd like to have an open API that people can use, can consume to build apps or to use that. But we also want people to do their own analytics if they're interested in this topic. So they could collect the raw data from us to work in a citizen science project, for example. So not official science, as in not only science by universities, but rather by individuals themselves or communities themselves. And lastly, we would like to, it would be cool if we could use this application also for ISO certification. Companies oftentimes have the requirement that they need to be environmental friendly. And this ISO 14000 helps them with that definition. So they need somehow to be able to measure the combustion output of factories, for example, and this network could help them with this. Lastly, security, of course, an important aspect that is usually, well, shouldn't be neglected, but is often a bit neglected. It's also why it's at the end. It's not the most exciting topic for most. But it's important here that not all the information should be public. We have to be careful about what we share and what we don't share. As I said, pollution levels for factories might be sensitive information that shouldn't go immediately out to the public. And there's also another aspect to it, and that is remote control. These devices that we would like to build, they're out in the open somewhere, and they are fire hazard. They have batteries. They could ignite, like the fear is on airplanes when you bring your mobile phone or your battery charger with you. the same issue applies in the field. If you leave it somewhere unattended, it might catch fire. That will be an issue for us. And so we have to take that into account as well. So that's the product vision. A long story, way too much to do in a small community project. And so we have to narrow this down and come to like a minimum value product. How do we accomplish this? So our innovation experts helped us this. They brainstormed with us. Let's focus on one persona, one type of user that we would want to service, that we see as our best example for somebody to use our product. So we identified that this is going to be John Doe, the typical, like, ordinary person, but a John Doe that does sports. This John Doe is interested in going running after studying or after work or on the weekends, and he doesn't want, when you do intense sports, your lungs open up and your intake is much higher than usual. And so pollution during that time really matters. And so we thought that, especially for a sporty John Doe, this would be very interesting. We could help him planning his sports regime, planning his routes, by predicting pollution forecasts, or by predicting pollution and showing forecasts. And so we came to our MVP. We want to have an independent remote sensor, like a device that collects these pollution levels, which connects to our cloud. And when we decided we use LoRaWAN here, and I'll explain it in a bit, which connects through a Things network to our cloud. We want to be able to monitor that information that comes in, and we want to visualize that on a map. With that information, we'd like to combine that with weather data to predict pollution levels at the next day or the next following days, and provide that information through a responsive website. So that, in essence, is the scope of the project that we decided to pursue in this stage. So, and this is also the scope of what I'm going to tell you about here now in the remaining slides. So before we start, we need to decide how we're going to organize ourselves. So we have a group of people, a group of enthusiasts from different backgrounds. Some are hardware technologists, some are industrial designers, some people are more project leaders or managers, or even from sales. There are a lot of developers, of course, people with UX experience. How do we manage ourselves so that this would work efficiently? So we decided we're going to follow a self-organizational approach, holocratic, in the sense that we just identified the groups that were necessary to build this product. And what skills are required for those groups. People then could decide for themselves to work in a particular group. They didn't have to have the skills. This is not just about building a product, this is also about learning new skills. And so if you are, for example, a UX specialist, but you wanted to do more development, you could do that. You could be a member of the development group. Of course, there needed to be leadership within the group. There needed to be sufficient skills in order to actually build something, because otherwise we won't get anywhere. But this is how we organized ourselves. We defined groups, and people decided for themselves where to attribute. And this worked really well. It naturally grew. There was a sense of responsibility and commitment. People ensured that there was a sufficient level of skill in each of the groups. And the communication between the teams was fluent. As in, there was no central organization that directed communication lines. No, people just talked to other people whenever it was necessary. And for such a scale, and we talk about a community of 30 people here in total, not full-time, but 30 people that contributed to this project across multiple countries. And this worked very well. And then, of course, in the center, we have our repository where we all put our work in. So this is how it looks like. This is how we set ourselves up. Before I'm going to show you the technical aspects, let's go a little bit into theory. What is actually pollution? What is particle pollution? We actually talk here about particle matter, which is shortened to PM. And it's a mixture of airborne solid and liquid droplets or particles that reside in the air. So they, like I said, they're airborne. And they come from various sources. They can be actual dust from roads, for example. They could come from combustion sources like factories, cars. Also, forest fires are a typical source. In Africa, for example, where people still cook on wood or coal, you see also a lot of air pollution. This is a different source than we see here, but it's the same. And pollution is heavily influenced by two aspects, weather and terrain. So on a hot, humid day, when there is no wind, the particles stay in one place and they just stay in the air. And you see that, for example, here in the picture in Paris in a summer where lots of smog caused by all these particles in the air because it is a hot summer day and there is no wind. Terrain has an influence because when particles are in the air, it matters what the temperature differentiation is. And so, for example, if you have, especially in winter, when you have a valley like in Zurich, there's often a temperature inversion, which means it's colder on the ground than it's in the higher up in the air, like a kilometer up in the air. And which this makes for the particles to stay below the temperature inversion level, which means that they stay in the valley, they don't move out. You see that with fog a lot as well, which is not the same effect, but it's similar. But the same for these dust particles. And so terrain makes a lot of difference. It also guides the airflow, right? Which usually in valleys, there's quite a bit of wind, but it really depends on the direction and the layout of the valley. When we talk about our health, we're primarily concerned with the two smallest particles, or two smallest groups of particles here, the soot particle and the dust particle. The dust particle comes from, which is called PM10, which is 10 millimeter in size, which is about a fifth of a human hair. They come from combustion sources and are the main contributor to the pollution here in the Western world. Right? And the other particle comes from that's much finer. They come from fires and from cooking, like in Africa. But you also have it here, because of course we also have forest fires here, or just regular fires. And so the PM2.5 and the PM10 particle or the groups are what we're concerned with, and this is what we want to measure and also predict. So with that theory in mind, how do we create our application? How do we create our product? And so what we need is a sensor on the very left that collects these air particles. We connect that to our backend through what is called the Things Network, which is an IoT network that helps us manage and control the data flow from the device to the cloud. So this is more or less out of the box. It's easy to use. We don't have to create it ourselves. The backend uses open weather data and combines that with the sensor data and provides that to the predictor to make its forecasts. And then the web app displays that information on a map and provides that to the user. This is the overall scheme of how we envision our product to be. So let's dive now into these individual components and see what we actually did, how we created these. The sensor network. So, like I said before, we needed a sensor that collects these two groups of air pollution particles, the 2.5 and the 10 micrometer. That sensor is connected to a microcontroller, which we have programmed with using the Arduino platform, and so that we can control the sensor, we can control that information, and we can control how we send it. We use LoRaWAN, which is a low energy, long range and low bandwidth radio technology broadcasting system. It's basically a WAN, like a wide area network, but using low frequency radio waves. This allows us to send the data up to 10 kilometers. And so we could have our sensor somewhere in the woods or on the road, have it send that information through using LoRaWAN to our cloud. We'll have the Things network, which contains a gateway that collects this data that comes in through these radio frequencies, and forwards that. It's more like a broker. It forwards it to the cloud, and we store that in a cloud service that we host in a Docker container. That's built upon the TIC stack, and the TIC stack is it's a combination of different components. Here we are primarily interested in using the influx DB, which is a time series DB. We could just basically receive the information, store it in that database, and it's available as a time series. So we designed it and then we created it. We see here the sensor, the SES011 sensor, which has a fan, the black thing on top, and it has, I don't have a pointer here, or do I? Maybe I do. I'm not sure. I'm not sure I should touch it. And it has an opening on the bottom left, this gray element there, which is the actual sensor, the opening that takes in the airflow, and then inside the box the measurements take place. This sensor is connected through a serial cord to the microcontroller, and the microcontroller has this LoRaWAN radio on top. It comes with a battery, so we can have it independent. We don't need to hook it up to the electricity network. And because this has to be installed outside, we need to have some housing. And we decided to create a box for this. Now, we could just create the box by sawing and gluing stuff together, but it would be much more fun if we just use a 3D printer. And so we bought a 3D printer, which just arrived, I think, like 2 months ago. We unboxed it and put it together, and basically designed the box based on the specifications from the hardware team. So this box needed to have an opening for the fan, of course, for the airflow. It needed a hole for the sensor on the back top left, and there's a little hole for a plug to charge the battery. Because the battery doesn't last forever, the one we have now, I would say, it runs out in about a month. Our hardware is a bit inefficient, but it's still a prototype. And then we printed it using the Ultimaker 3D printer. And so this took about, I would say, 8 hours to print altogether. I think we went through 2 iterations where we made one mistake in the design and we had to do it once more. But yeah, it's printing dust, printing the box from dust. And this is what it looks like in the end. You see the dust box here and the bundle of hardware on the right. And I actually brought it with me. This is the box, the 3D printed box, and with the hardware inside. It's glued together or taped together. You can have a look at it later at the lounge, so I'll leave it there if you're interested, just to see the components, or maybe just see the box. This is still experimental. It's not perfect. We have to go through another iteration, I think, to make this actually workable outside. But the process works. So now with that data available, now that we are able to collect these particles, we can actually start doing our predictions. And we'd like to use machine learning for this. And before we dive a bit into the details here, let's recap. We need to predict both the 2.5 and the 10 micrometer particle sizes for a specific location. We decided to just focus on one location rather than different locations for two reasons. One, pollution is high when there's no wind, so there shouldn't be much movement of particles from place to place. If there is wind, then the particles disperse. They move into the upper, or higher up in the air, I should say. And secondly, we don't want to overcomplicate this. It's an MVP, not a full product, and so let's focus on the essentials here. So we decided, let's do predictions for one specific location based on the information that we got from that location, and let's combine that then with the weather data to see if we can, how that influences our predictions. For the weather, we want to use temperature. Like I said, the hot, humid day makes a lot of difference. For that also, therefore, humidity is important. Winds, speed primarily, direction not so much. And it's of course also important to realize what time of day, or what day of the week it is. Like in the weekend there's less traffic, and so there's probably less pollution. And the day of the year as well, because weather has a seasonal pattern. It makes a difference whether we talk about winter or summer. We identified that we needed about 6 months of data for our prediction algorithm to be at least a little bit reliable. And we need to have, and we decided that the prediction would use a 5-day window for its observation. So we would look 5 days in the past to do the predictions for the next, say, 2 to 3 days. Now, we do have this sensor, this device, but we don't want to wait 6 months for it to collect data before we can start playing around with our AI, with our prediction model. So we decided to go to another source. We went to luftdaten.info, which is a German initiative. It's also a community that builds these sensors, similar sensors. And it measures the same values, the 2.5 and the 10 PM values. And they're primarily in Germany, less so in Switzerland. You see a few nodes here if you look closely around Zurich. So there are a few sensors here that we could use, but primarily it's in Germany. But we had a look, and we identified a sensor in Zurich that we could use for this, and that had sufficient data that goes back back 6 months. That is reliable and consistent. And so there's no gaps in the data. It doesn't look strange. Like the measurements look correct. And so we consider this as a good source for our machine learning data. The weather data we took from the Open Weather Map. This provides, they provide historic data on weather, on all aspects that we're interested in, especially temperature, humidity, wind speed, granular enough for us to work with. So granularity here is once an hour, which is also what the sensors, the dust sensors provided. And so this is workable. So unfortunately it wasn't free, so we had to purchase this, but it's a one-time purchase. Shouldn't be, that was not so much of an issue. And then we started to build our model. We used Microsoft Azure Machine Learning Studio here, which is a WYSIWYG plug-and-play environment to do machine learning. You could just drag and drop the individual machine learning components on it. Very easy. You still need to know what you're doing, but you don't have to program it yourself. You can just easily, quickly play around with different aspects and just experiment. We split up our data set between a train and a test set, because with the train set we could validate whether our algorithm was actually correct. And we trained this with a neural network with 200 iterations. And the results were okay. But there was one limitation, and there was no possibility to together predict both 2.5 and 10 micrometer particles. So it doesn't support multivariate regression in that sense. which is a limitation and which significantly hinders us from providing true, reliable predictions. And so we decided to move away from the Microsoft Azure Machine Learning Studio. It was good to try out, but it was not sufficient to produce something or to create something that was usable for a product. So our second attempt was to use Google's TensorFlow with Keras and scikit-learn. And here we created a multi-layer neural network with I would say the standard configuration for such a network. I'm not going to go into details here. If you're interested, I could give a bit more background later. So we trained this, again, we did the same thing. We split up the data. We iterated that 200 times. But this did provide a two-variable output, right? So this provided output that both had the 2.5 and the 10 micrometer particle predictions. So with that reliable predictor available, we could finally integrate this into an actual product. So to reiterate what we had, if you remember the architecture from before, we had the sensor that is connected to the Things network, which acts as a broker that sends that data, and sends the particle data to the cloud. So so the Things network is actually on the, let's say, internet. It has a gateway that receives these radio frequencies, and it forwards that information it's a broker that forwards that information to our cloud service. And our cloud service is this TTN gateway, which we call, which is implemented with Go. And what it does is it's actually also, it's just a gateway. It takes that information and stores it in our database. And that database sits in our cloud environment. We then created an enhancement service which executes a cron job and identifies whether there is new data in the influx DB, or maybe collects a bunch over a whole day, and connects to the Open Weather Map Open API to get the weather data that we need, aggregate that together, and then we store that in our relational database, this PostgreSQL database. The prediction service then takes that data from the PostgreSQL to do forecasting. This is not an on-demand job. This is a scheduled job. You need forecasting once a day, so we schedule it overnight, for example, to collect that information from the database, do our forecasting, so execute our model on the new data that we have, and then store the results back. And then lastly, we have a web API, or web UI or web application that combines the information, both the historical information from the weather and the sensor, as well as the prediction values from the prediction service, and provides that to the user. So everything in this rectangular box here is the cloud. We've hosted this on Microsoft Azure. And each of these components, the red and blue ones, are actually individual components. They are hosted in a Docker container, and they're orchestrated using Kubernetes. So this is also very scalable. We can easily start or stop these services. They're independent. And so if the gateway goes down or if the enhancement service goes down, we still have our web UI available. We still have a prediction service available, although if it doesn't get any data, it's not going to compute anything new, but it's still running. And then lastly, we created our website, our progressive web app, that would show this information live on a map. And this was implemented using HTML5 and Angular with TypeScript. And then the back end of the service was implemented in .NET Core. And I'll give you a little demo of how this looks. Let's see if we can start it. There we go. Yeah, there we go. Okay. So here we go. Here we are in Rapperswil. There's no sensor here. I brought it here, but it's not working. It ran out of battery. Our sensor just consumes whatever it wants, and we cannot shut it down. We really have to unplug it. And we forgot to do this, and so it ran out of battery. But we do have a sensor as well in Zurich. And it provides both historic and prediction values for these dust particle groups. So you see here in green the larger particles from the combustion sources, as well as the values in gray from more like forest fires, etc., or fires or just dust. And the prediction service, based on the information in the weather data, it does its predictions over a few days. And so you see here the effects of the predictions. That have been calculated by this service. We also have a few more locations. I want to zoom out a little bit more. There we go, a bit more. So, okay. All right, so we have a few more devices. So we created actually a few more of these boxes, and we shipped them out to our colleagues that were working with us on this project. So we have a team sitting in Bratislava, for example, that are actually working on this. We have a team in Romania, and we have people in Spain, all part of Fernie. And they have these boxes running as well. I'm not sure whether that information is live. I haven't checked. But this is how it looks like, and we can visualize it on the map, indicating how the pollution levels are. I think if you look at Switzerland, for example, if you go back, zoom in, we also have Lucerne. Lucerne looks a bit better. It's not as polluted as Zurich, which makes sense because it's smaller and it's closer to the mountains. You would expect the air quality to be a bit better there. Right. Just to wrap up, this is the technical part. So I'd like to give you a little feel of the community itself. So what we did was, we came together as a group of people that wanted to work on this cool project, and it would also be great, of course, if you could just meet in person and work closely together, because that's much more efficient usually, and also just much more fun, right? So we organized a hack and hike, which is a weekend event in the Swiss mountains near Visiflu, near the Lake of Lucerne, not so far away from here, where we just stayed at a mountain hut. We brought our own router with us, so we had internet, a 4G router, and worked together. Colleagues from Bratislava drove all the way to Switzerland as well, so they drove the whole day to meet us, to join us on this project. Yeah, and I mean, it was just a great event. It was nice to network, nice to be together, work together, exchange ideas. Really helpful in a self-organized environment where there are individual people, individual teams, and communication just happens as required, right? So you see here part of the team. This is the end of the event when it was again sunny and we could enjoy the weather. We also hiked a bit, but it was, as you saw on the previous slide, cloudy, even rainy. Actually, the day before, it was raining so much I was completely soaked when I arrived. But nonetheless, I mean, it's great. It's great to just be in the fresh air and work on such a project. And I want to part with you just to show you, give you a bit more experience on this by just playing a video of that event. And I hope the sound works.
So I've been involved in Hack and Hike for the last 4 years, and really impressed by the energy everybody gives to this project. This time we're doing a dust measurement network with machine learning and lots of different technologies. I'm not a programmer myself, but I sometimes like getting my hands dirty doing some coding. So it gives me a really good opportunity to learn about new coding things.
Du bist noch nie an einem Hack and Hike gewesen, dann kann ich dir wärmstens empfehlen, auch mal teilzunehmen. Spannende Diskussionen zu technischen Details, dazwischen wieder wandern, nachher gutes Essen. Ja, ich würde mich sehr freuen, dich da mal zu begrüßen und mit dir die Tage zu verbringen.
And with that, I'd like to part. We have our work online at the GitHub repository on this link. So if you're interested, just come to me afterwards and ask if maybe you could have a look or contribute. We'd be happy to have people working with us to actually push this forward. It's still, because the product is, or the application is not yet a product, it's still a prototype. It's working, the moving parts are working, but it needs to be polished in order to finish. And I'd like to thank you all for listening, and if there's any questions, I'm happy to take them. Otherwise, you can ask them at the lounge where I'll be, or during the lunch break, or a coffee break, or something.